Hello, we continue with this chapter 3-4. We have three methods to tuning open loop transient response method, Ziegler-Nichols method, and frequency response method. And the first one, open loop transient response method. So this one, this method referred to as a process reaction method. Also divided by these two engineer. The basic approach is to open the process control loop so that no control action occurs. Disconnect the controller output from the final control elements. This requirement that's called open loop, but sometimes we will later discuss this one not applied to any control system. In some cases, we don't have the option to open a process control loop. This method, so basically, so you can see the delta CP is the changing controller variable arrow. That's the delta CP, and this one is L, the time domain. This is time axis. We have the L and the T. And these two will be, these three, WCP, L, and T will be used to the calculation. Once we have this one, so you can see this is the response loop line, tangent line to the response curve. And then we will see this one goes, we calculate N, and then we do the, for proportional control mode, we will use the Kp equal to delta P over NL, delta P, so also we define the controller variable change, so that's basically what's the input signal will change, will causing the response change, so that delta P is basically what the controller variable change. And then there is this expression to calculate for proportional control. For proportional integral control mode, we have two factors, and then for the PID control mode, we have three factors to select. And this is example 1 in this chapter. This is corresponding to our question 6. So basically, for this figure, this question is given the result of the 9% controlling variable change, give a process reaction graph as shown. So you can see in this, we know delta P is 9%. And from this figure, we measure the L. That's basically from this tangent line. The point here is 2.4, and then we measure this one. Just assume this is 7.2. So 7.2 minus 2.4, we get T equal to 4.8. And the delta CP here, that's from 0 to just say this is 3. And we get 3.9, very close to 3.9. Therefore, we get this, calculate this N is this value, and then we can see we do the PID controller, then we have this Kp is 1.2, use delta P over NL. So put the values here, Ti, Td. And then second method is called the Ziegler-Nichols tuning method. So remember, that before we have that subsidence ratio, let's basically use that subsidence ratio. So basically subsidence ratio is say the first peak to second peak, this ratio. So peak A over peak B is 1/4. This is the Ziegler-Nichols method. We want the system to be at least is 1/4 quarter wave. And this one is basically for this I think question 7 is about asking what steps we should follow, and that's the 4 steps here we need to follow. So that's basically what we do is using this method we were so that's basically how we measure those values, and then we get a perfect sine wave. So that's we have a steady oscillation, and then there is a note the critical K0, that's the gain K0, and then we measure T0, that's the period T0. And once we have those K0, P0, K0, T0 measured, we get this proportional control can be only that's this value PI is these 2 value, PD is these 2 value, and the PID were set. So all those values are setting in this table. I think question 8 is similar to this 2 question. And the last one is a frequency response method. And here we have another 2 rules. Remember in the we talked about the criteria of a control system. There's 2 rules, but here this is additional. So rule 1 is a system is stable if the phase lagging is less than -140 degrees at the unity gain frequency. Remember before we say -180, but here we want it's limited to a smaller value. That's because we want to get an optimum control system. This is the very basic requirement is at least we cannot go to -180, but this is further change to -140 degree. I think in the quiz there's a question asked if these 2 rules, rule 1, rule 2, is conflict with our system criteria. That's this one. So we have a criteria rule 1, rule 2, but here we get the additional 2 rules. These 2 are not conflict with each other because this one is we want the system has a optimum performance rather than the in that session that's the basic requirement. So rule 2 is if the gain is 5 decibel below unity, that's again is about 0.56 when the phase lag is -180 degree. The system is stable. So that's basically additional requirement. So tuning is basically so you can explain. So you can read this one. Is basically we use this example is to at unity gain. What's the phase angle? So that's basically on this point. And then at -180 degree, what's our gain? So remember we require 0.5 at this point, but this value is obviously larger than 0.5. So that's basically where so can look at this example solutions. That's basically we want this one to move down some values and then to fit our rules. These 2 basic rules. And also there's talking about, remember before we have talked about the PID controller, it has the derivative mode has a positive phase angle. So that's sometimes so you can see if we want the phase angle that response is better than if we get a -180 degree, then you probably consider to add the derivative into your control scheme, so it will get our phase angle that response give us better performance on that session. That's all for the material we cover. This one. Take a look at the assignment. So assignment, so basically we talk about those 6, 7, 8, 9 is corresponding to section 3, 4, and question 1 to 5 is basically the section 3, lecture 3. That's this one. So question 1 is basically corresponding to the page 16 in our section 3's notes. And question 2 is just a 0 pole. That's listed. It's 0 pole plots. We did this one in the week 1's quiz. And the third question is so we did this one in the quiz 2. So basically you change S into J omega, and then once we have the gain, I think there's a couple problems with this question. So we go back to notes 3 on page 33, and this one is in the quiz 2. So that's one question asked for what's the frequency response function. This is G omega is our frequency response function. And then this is the magnitude. Magnitude is basically, even though this J omega is still here, but you can see the expression don't have J. So that's basically has x squared plus y squared. So that's basically we want to calculate the magnitude in the complex system. So the magnitude is it's not depend on J, only on omega. And then this question I didn't calculate phi. So what calculation here is you can see, look at this expression. Is this one only have a complex number, imaginary component, but 0 for the x component, real component is 0. So this one, because this negative here, so you can see we have always a negative 90 degree, because the in the complex number system, the x, y, so positive 90 degrees go up, negative 90 degree goes down. So this is negative 90 degree. So that question is similar. So once we have expression for J omega and phi omega, and then you can calculate for the omega equal to different values, omega 0, omega equal to 1, omega equal to 2, and omega equal to infinite large. So calculate the 4 values. And this is 2 sub-question, and the question 4 is 100 draw body plots. Go quick. So question 5 is on page 8. 100 draw the body plots. In 100 drawing of the body plots, so we already talked about on page 38, we get this one. If we have multiple terms in this expression, we can separate them into individual one, and then because we take a logarithm, so this different subsystem will be added together. So so this one is say so that's a basic transfer function and their body plots. So in that expression we have 1 over s term. So you can see we will have this body plots. This is the phase angle, and then there's another. Let's take a look back. So you can see this s 1 over s is and then there's another 1 over 2s plus 1. So this one is 1 over s, it gives us this one. Another one is this first order system. It will give us this expression. So the first one you can see its value is, of course, make sure this tau, so calculate this value. then you can add these two together, That's your overall body plots. Similar for the second question is also 2